Hello students, welcome to part 6 of the chapter Electrochemistry. In the previous parts we have seen or we have discussed about galvanic cell, and one of the famous galvanic cell is the Daniell cell. In the Daniell cell we had anode on the left and cathode on the right. Cathode had higher reduction potential, which is the copper half cell, and the left it is the zinc half cell, which is having lower potential, and the oxidation is taking place there. And when the two electrodes are connected by a voltmeter, it shows an deflection towards cathode, suggesting that the electron is flowing from anode to cathode. And the deflection shown in the voltmeter was 1.1 volt. And this deflection and the voltage means that the cathode is 1.1 volt higher than the zinc electrode or the anode. The difference between the two electrodes is 1.1 volt. Now I am going to connect an external potential. This external potential source will supply a potential to the anode. So the connection is in a way that it will supply a potential to the anode, that is to the zinc. And here you can see it is now 1.1 volt, means now this external source is supplying a voltage that is equivalent to 1.1 volt to zinc. What was the difference between these two? It was 1.1 volt. Now it is supplying that 1.1 volt to the 1.1 volt to the zinc. That means now the potential of both electrodes is the same. So what happens? First, the flow of electron will stop because now the potential of both the electrodes are the same. Now if you look into the reading of voltmeter, you will see that once when the potential is the same, the voltmeter reading has come back and it is steady now between both the electrodes. And once it is steady, then there is no reduction or there is no oxidation happening. Then they will disappear. That means the Daniell cell is now in equilibrium. Now let us see what happens if I am increasing this voltage. So this voltage is now supplying voltage to the zinc electrode. What happens if I am supplying a voltage excess of 1.1 volt? I have increased. Now you could see that a small deflection towards zinc. That means now the potential of zinc has increased. If the potential of the zinc has increased, then there is no equilibrium. Equilibrium is gone. Since this is having higher potential now, then electron starts flowing from copper to zinc in this direction. It was earlier in this direction when this had higher potential. Now it has higher potential due to this external source. Now what happens is, earlier it was anode, now it has changed into cathode, and this is anode. So cathode with a positive potential and anode with a negative potential. Now what happens if I am increasing the voltage further? The deflection is increasing. So what happens is, when an external voltage is applied which is excess than the cell voltage, the reaction reverses. That means now the reaction taking place is non-spontaneous. Earlier the reaction was spontaneous when there was no external voltage. When there is an external aid, the reverse reaction takes place. So the non-spontaneous reaction is taking place here. So this is now a device which uses electricity to carry out non-spontaneous reaction. In part 1 we had discussed about such a device, and it's called electrolytic cell. Electrolytic cell. Daniell cell, which was a galvanic cell, has now turned into an electrolytic cell because this Daniell cell is now under the influence of an external voltage. This is one type of electrolytic cell. There are different types of electrolytic cell that is constructed to suit to their different applications. One another type is this, which we had discussed already in part 1, electrolysis or electrolytic cell. Here two electrodes are connected to a battery. Positive electrode and negative electrode we have immersed in an electrolytic solution which contains positive and negative ions. Negative ions which has excess of electron will move towards positive electrode and will lose electron. That means oxidation takes place and hence it is named anode. On the other hand, positive ions that are deficient in electron move towards negative electrode and gain electron, which is reduction, then hence it's named cathode. You will see it from the animation. Negatively charged ions move towards positively charged electrode and positively charged ions move towards negatively charged electrode. So this is also an example for electrolysis, where electrolysis is taking place in one chamber. In Daniel cell it was taking place in two different chambers, and also you will see that sign of electrode changes. Here anode is positive, whereas in Daniel cell anode is always negative. So it is a very good example that the sign has nothing to do with the name. It is the process that decides who is anode and cathode. Oxidation is always anode and reduction is always cathode. Another type of electrolysis is given here. So this type of electrolysis is used for the purification of metals. So I have as negatively charged electrode a pure strip of metal. Here I am using this technique to purify copper. So I have a pure strip of metal, and on the right hand side I have an impure strip of copper which is called blister copper. Production of blister copper you will learn in the metallurgical process chapter. For now we will see this process. So this process is actually used for the purification of certain metals. Here for instance copper. So blister copper is the impure form. What happens is, once this battery is switched on, this electrode gets a positive charge and this will get a negative charge. So Cu on this electrode will go into this solution as Cu2+. That means Cu loses electron. So this is oxidation electrode. So what's its name? Oxidation electrode is anode. Cu that entered into the solution, Cu2+ that entered into the solution as a positive charge, it will get attracted towards the negative. It will reach here, it will receive electron and get deposited here as copper metal. It will get deposited as copper metal. Since it is gaining electron, the process here taking place is reduction, and hence negative charge electrode in this case is cathode. So with time you will see that this electrode is getting slimmer and slimmer, whereas this electrode is getting thicker and thicker. Why it is getting slimmer? Cu is going to the solution as Cu2+. Why it is getting thicker? From the solution Cu2+ is getting attached to this electrode as metal. So we will see this process happening as an animation. Once the switched on, Cu2+ from this electrode is going, and you will see that it is getting thinner and it is getting thicker. Once it is finished, you will replace it again next. So in the process, this impure metal has a lot of impurities inside it. That impurities will fall down beneath that electrode. This is anode, and the impurities coming from that anode is called anode mud. Anode mud, which we will learn later in detail. So this is also a process of electrolysis. This process we will learn again in the later part of this chapter. So I just showed this to show you that there are different types of electrolysis process that are designed to suit their needs. So we will look into electrolysis in general. In electrolysis, passage of electricity is mediated by two medium. Let's see how. Inside the electrolytic solution, passage of electricity or electricity is mediated by the movement of ions, and outside it is by the movement of electrons through this external wire. So this conduction is called metallic conduction, and this conduction is called ionic conduction, and the conductors is called electronic or metallic conductors, and this is known as ionic or electrolytic conductors. So we have two conductors. On the top we have electronic or metallic conduction. What is responsible for the electricity movement is movement of electrons. Inside the solution it is ions, and hence it is called electrolytic conduction or ionic conduction, and the movement of ions is responsible for that. So we have, in electrolysis we have two types of conduction. We have learned a lot about this type of conductors in physics, but we haven't learned much about this type of conduction. In this chapter we will learn a lot about this type of conduction, because it is very crucial to understand this, to understand the process of electrolysis. So we will make first a comparative study between the properties of electronic and electrolytic conduction. In electronic conduction, it is the movement of electrons is responsible for conducting the electricity. The second thing is, it depends on the nature and structure of the metal. So conductivity of a metal depends upon the number of valence electrons. Details of this part we will see in D block elements. However, in short we can say that depending upon the metal, the conduction also differs. Conduction is inversely proportional to temperature. As the temperature increases, conduction decreases. That means if you compare the transmission of electricity in summer and winter, in summer you will see lot more obstruction or resistance to the flow of electricity. Fourth point, conduction will not change the composition of the conductor. So if the conduction is in the range of conductor, normally metallic conductor remains the same. It is the same, the composition is the same before and after the conduction. If you look into the properties of electrolytic or electrolytic or ionic conduction, conduction is due to the movement of ions, as we have seen. It depends on the ionic size. So as the size of the ion increases, electrolytic conduction decreases. Their solvation, more the ions are more the electrolyte is soluble, more will be the conduction. Then the nature of solvent, like viscosity, if the viscosity is higher, the conduction will reduce. So it depends on lot of these factors of solute and solvent. Next is, conduction is directly proportional to temperature. So this is exactly opposite to what we saw in the case of metallic conduction. Inversely proportional to temperature in the case of metallic conduction, but it is directly proportional to the case of temperature. Why? Can you deduce it? Yes, it is because as the temperature increases, the motility of the ions increases, or rapidly the particles in the solution moves. This will increase the conduction, and also increases with solution concentration. Why? Because as the number of ions increases, which are the carriers of electricity, conduction also increases. And the last point, unlike metallic conduction, here the conduction alters the composition. So when there is a conduction, there are chemical reactions taking place. That means reactants are getting converted into products. So reactance diminishes and products are formed. So there is always a change in species accompanied by the electrolytic conduction. So the composition of the electrolytic solution is changing. So this is a comparison of the properties between electronic conduction and electrolytic conduction. Next we will look into general properties of conductors. First is resistance and then it is resistivity. In lower classes we have learned about the famous relationship V is equal to IR. Voltage is equal to current into resistance. If you write it, you can also write it like this: R is equal to voltage by current, or R is equal to V by I. Resistance, the unit of resistance is ohm, which is the SI unit, whereas if you take the base unit, it is this shown here. Resistance of a conductor, as we have learned in the lower classes, the resistance increases with increase in the length of the conductor. That is, it is directly proportional to the length of the conductor. Resistance is directly proportional to the length of the conductor, but it decreases with increase in area of cross section. Resistance decreases as there is an increase in the area of cross section. So R is proportional to L and inversely proportional to A. If you remove this proportionality sign, I have to add, or I have to make one change, that is, I have to add one proportionality constant, that is R is equal to rho into L by A, which is a Greek alphabet representing resistivity or specific resistance. Rho into L by A. This rho is a constant for a conductor at a particular temperature and pressure. So R is equal to rho into L by A. Rho is a constant, it is a proportionality constant. What is rho? Rho can be defined as the resistance of a conductor whose length is 1 meter and area of cross section is 1 centimeter or 1 meter square. So imagine that there is a conductor whose length is 1 meter and its area of cross section is 1 meter square. I am substituting these values in this formula, that is R is equal to rho into 1 meter, then R is equal to, this will remain as unity, is equal to rho. So rho can be considered as resistance of a conductor whose length is 1 meter and area of cross section is 1 meter square. So these dimensions for rho are fixed. That means if you are speaking about resistivity about conductors, that means it's always referring to a conductor whose length is 1 meter and area of cross section is 1 meter square. This will be helpful to compare resistance between different materials. Since its dimensions are fixed, you can always compare the resistance between two materials to see which is more resistance or to see which is less resistance. Now unit of rho, from this equation it is clear that it is ohm meter. Unit of rho is equal to ohm meter, because when this move to the left hand side, this will go to the numerator and this will come to denominator, where 1 m will cancel out and the remaining m will remain in the numerator. That is, rho is equal to ohm meter. Okay, next so we have found two properties here. One is resistance and other one resistivity. They are related to each other as R is equal to rho into L by A. Next is properties of conductor. In this we have conductance and conductivity. Conductance denoted by the symbol capital G and conductivity denoted by the Greek alphabet kappa. So it's a Greek alphabet and it is read as kappa. So from the last slide we know the relationship between resistance and conductivity, resistivity. R is equal to rho into L by A. Now here the property is given, conductance is a reciprocal of resistance, because resistance means it resists the flow of electricity through a conductor, whereas conductance means it allows the flow of electricity through a conductor. So these are two reciprocal terms. Similarly, rho and conductivity are two reciprocal terms. So you can say conductance is a reciprocal of the resistance R. G is equal to 1 by R. So if this is resistance, I can just inverse this formula, like G is now equal to A divided by rho into L, A divided by rho into L, because G is equal to 1 by R and R is this. So G is equal to A by rho into L. As I said, conductivity is the inverse of rho. Conductivity is inverse of rho. Then 1 by rho I can call it as conductivity. 1 by rho is equal to conductivity. Therefore, G is equal to K into, so instead of 1 by rho I am replacing it with kappa, kappa into A by L. Unit of conductance is ohm raised to minus 1 because it is 1 by R, so ohm raised to minus 1. Or you can write instead of this, just read it in the reverse order, mho, MHO, mho. Ohm is read as mho, or most simply, most often it is expressed in terms of Siemens. It is the same as ohm raised to minus 1 and mho. So you can go for any of the three if you are representing G. So again, like resistivity, conductivity is a constant at a particular temperature and pressure. How to get the value for conductivity? It is conductance when area of cross section is 1 meter square and length is 1 meter. We will see here 1 meter square and 1 meter, then G is equal to kappa. And unit of kappa is equal to is Siemens meter is to minus 1. This is just inverse of resistivity rho. Resistivity was ohm meter, and the inverse of it is ohm raised to minus 1, meter raised to minus 1. Instead of ohm raised to minus 1, I can go for Siemens. Now, based on conductivity, so far we have studied properties: resistance, resistivity, conductance, and conductivity. And based on conductivity, we can classify the materials into 4. First one is conductor, materials with very high conductivity. Examples: metals and their alloys, non-metals like carbon black, graphite, and some organic polymers. So almost all metals and their alloys like steel, etc. And non-metals like carbon black and graphite. No too much non-metals will conduct electricity, but few like carbon black and graphite can conduct electricity. And similarly, some non-metals like organic polymers can conduct electricity. On the other hand, insulators are materials with very low conductivity. Example: glass, ceramic, etc. Ceramic are the materials that we often use for power transmission. They are perfect insulators and will not conduct electricity. In between these two, there is a range of materials between conductors and insulators called semiconductors, have moderate conductivity like silicon, doped silicon, gallium arsenide, etc. So silicon, doped silicon, gallium arsenide, etc. falls under the category of semiconductors. And a fourth category are called superconductors. In earlier times, metals and their alloys at low temperature were found to conduct electricity without any resistance. We call it as zero resistivity or infinite conductivity. So zero resistivity and infinite conductivity means the material will allow electrons to flow, electricity to flow without any resistance. In earlier times, it was metals and their alloys at low temperature. Later, it was found that certain mixed oxides and a number of ceramic materials can also act as superconductors even at room temperature. So we have a table here to show or to compare the conductivity of certain materials. So conductors like these metals and certain non-metals have a range from 120 to 2100. Siemens meter is to minus 1. So 120 to 2100. Whereas for insulators it is 1 into 10 raised to minus 16. Siemens meter is to minus. So that is the range difference between conductor and insulator, and in between them, like value of 2, 1 into 10 raised to minus 7, 1.5 10 raised to minus 4 silicon, they range as semiconductors, that is ranging between high values and very low values. They are semiconductors. So all these category belong to metallic conductors or insulators, whereas the other class which we discussed in electrolysis was electrolytic conductors or ionic conductors. They are given here. Their conduction is much lower than that of solid conductors. Regardless of solid or metallic, how to calculate resistance of a conductor? Today we have a lot of different instruments, different devices, just working on your fingertip to know the resistance of a conductor. Earlier we used to use Wheatstone Bridge to calculate resistance of a conductor. So let's see how does it work. In Wheatstone Bridge, a battery is connected to 4 different resistance like this, one end here and one end here, and among the 4 resistance, R1 and R2 are in series. They are connected in series with the battery. Similarly, R3 and R4 also connected in series with the battery, but both these series connection R1 R2 is parallel with R3 and R4. And these two series connections are connected by a wire to know the potential difference between them. So a device here senses the potential difference between these two series connections, R2 R1 and R3 R4 connections. And at the moment the voltage difference shown is 1.02 volt. Now what are these resistance? In the Wheatstone Bridge, R1 is a variable resistance, which means that I can change value of resistance by knowing the values. I can change, but still I can know the value of R1. R2 is the resistance that is unknown. That means this is the resistance of our conductor. Here is where I used to keep my conductor to calculate its resistance. This is unknown resistance, whereas R3 and R4 are known resistance or resistant box. These values I will know. So I know these resistance R3 and R4, and they are connected in series, whereas other series R1 and R2, in this R1 I can know, but I can also at the same time make variations in this resistance, and R2 is unknown and cannot make any variation in it. And this is what I have to find out. So in order to find out, I must first make this voltage, or there should not be any potential voltage difference between the two series connections. Right now there is a voltage difference of 1.02 volt. I am trying to move this knob up to see the difference. So when I moved up a bit, voltage decreased, so I moved further and the voltage here is now 0. If the voltage difference between the two series connections is 0, then there exists a relationship, that is ratio between these two will be equal to the ratio between these two series connection, and it's given like this: R2 by R1 is equal to R4 by R3. From this, though this is variable, I can know the resistance. Since I am using a resistance box, I may able to know the resistance of this value. So from this formula, only one resistance is unknown, R2. Since I know all the other three, it is possible to calculate R2. R2 is equal to R1 into R4 divided by R3. Now I have the formula for resistance of a conductor. R is equal to rho into L by A. So resistance can be calculated. Resistance of this conductor can be calculated here using Wheatstone Bridge. If I know the length of this resistor, and area of cross section I can substitute into this formula. Now I know R from this Wheatstone bridge, L and A is known, then I can calculate resistivity. If I can calculate resistivity, I can calculate conductivity. How? 1 by rho is equal to conductivity. So this is all about metallic conductor. But if I am using an electrolytic conductor, which is my prime importance in this chapter, to find out the resistance of an electrolytic conductor, I face two problems here. What are those problems? Wheatstone bridge and electrolytic conductor using a DC current. So Wheatstone bridge is using DC current. It will alter the composition of electrolytic solution. As we know, in a DC current, one end will be positive and the other end will be negative. And as a result, reaction takes place, and the positive and negative reduction and oxidation takes place, and positive and negative end will see certain chemical reactions happening there, and there will be a decomposition of electrolytic solution. So composition will be altered. That means even if you measure the conductivity or resistivity, it will keep on changing. So this is a problem. Second problem is like you cannot connect electrolytic solution like how you connected a metallic conductor. So you can easily connect a metallic conductor using its two ends, but it is not possible to measure electrolytic solution like that. Why? That we will see in the next slide. So to overcome all these difficulties, I am using a modified Wheatstone bridge for electrolytic solution. First modification is with reference to this one. DC current alters the composition, so I used AC current. What is the advantage of AC current? It always shifts the polarity. So that means there will be no decomposition of electrolytic solution. Second is specifically designed conductivity cell is used to connect the Wheatstone bridge. Why do we need a specifically designed conductivity cell? That we will see in the coming slides. First we will see how to calculate resistance using a modified Wheatstone bridge. Here I have the modified Wheatstone bridge. So you can see that instead of a metallic conductor, in the unknown resistance part, that is R2, I have a conductivity cell. Why do I need a conductivity cell? This we will discuss later in the next slide, I would say. So now I have all those resistance, but this resistance is in the conductivity cell. If I want to measure the resistance of an electrolytic solution, I simply dip this conductivity cell into it like this. I have the electrolytic solution in this beaker. I dip this conductivity cell into it. Now making the value 0. Already I know R1 is variable, R4 and R3 is known, and R2 is unknown. From the relationship I can calculate R2, which is the resistance of this solution. R2 is known. Thus resistance R of the electrolytic solution is determined by the modified Wheatstone bridge. Now into this equation, if I am substituting, I have resistance. But if I want to know resistivity and conductivity, so first I want to know resistivity from this equation. I have resistance, but what I need is length and area of cross section. For an metallic conductor, length and area of cross section is easy to measure, but in the case of electrolytic solution, it is difficult to measure length and area of cross section. For that purpose, I am using this conductivity cell. Even for conductivity cell, it is difficult to measure length and area. So how I will solve this problem? Again, I have the formula R is equal to rho into L by A. I am bringing this rho here. R by rho is equal to L by 8. Rho shifting to the left hand side. Now I have rho in the denominator. 1 by rho is kappa. So I can write R into kappa. So 1 by rho is kappa. So instead of 1 by rho, I can write kappa. R into kappa is equal to L by A. And as we discussed, both L and A is difficult to determine. But L and A, if it is there, it will be a constant for this conductivity cell, isn't it? Yes, L and A, it is difficult to determine, but if it is there, it will be a constant, because I can measure the conductivity of all the electrolytic solution using this conductivity cell. I just have to replace the solution in this container and dip it. So I can use the conductivity cell for all type of solutions, and for that conductivity cell, L by A will be a constant. What will be changing? R and conductivity will be changing. Resistance and conductivity will be changing. L by A is a constant. So first what I will do is I will try to fix L by A. How can I do it? I will take an electrolyte with known kappa, known conductivity. Conductivity of electrolyte can be determined by some other methods, which is not that easy to do always. So if I have a solution with a known conductivity, I will place that solution inside this beaker, so whose kappa is known. So if I have a relationship, now the electrolyte that I am going to take inside this beaker is having a kappa value. So kappa is known. I have a known electrolyte here. Let's say it is potassium chloride. Its kappa is known. So I place it inside here, and I will measure the potential, and if it is 0, then I can find out resistance of this solution. So from this equation, next, resistance is known from the Wheatstone Bridge. Kappa is known, resistance is found out, and resistance is known now. What is the product of resistance and kappa now? It is L by A. That is L by A, which is a constant for a particular, which is a constant for this cell. For any cell, it is a constant, and it is called cell constant. L by A is equal to cell constant because it is a constant for a particular cell, denoted by the letter G star. G star for a cell is a constant. So I can instead of L by A, now I can write for a conductivity cell, L by A is equal to G star. Therefore R into K is equal to G star. Let's see a problem to see how they found out L by A from a known kappa value. You can see here resistance of a conductivity cell with 0.001 molar KCl solution at 298 Kelvin is 1500 ohm. So how did they find this resistance? From Wheatstone Bridge. From the Wheatstone Bridge, value of R was 1500 ohm. What is the cell constant? We have to find out G star. If the conductivity is given, conductivity of the same solution at the same temperature is 0.146. So this is a solution of known conductivity, and its resistance is found out using Wheatstone Bridge. Now what I have to find out is G star. So resistance is known, conductivity is given, I have to find out G star, and I found G star as 0.219 centimeter raised to -1. So it is its cell constant. Once if the cell constant is known, I can use this to find out conductivity of the solutions whose conductivity is not known. Let's see. Here is the formula. R into K is equal to R into kappa is equal to G star. R into means resistance into conductivity is equal to G star. Now I have again the same apparatus, but here this time this solution kappa is not known, conductivity is not known. So I want to find out conductivity of this solution. Conductivity can be found out if I know cell constant and resistance. cell constant for this particular conductivity cell is already fixed from the previous problem. So I have in the solution an unknown solution and a solution with unknown kappa value. Now using Wheatstone Bridge I am finding out the resistance, and I have these two values here. From previous one I have G star, and from the Wheatstone Bridge I have value for resistance, so that means resistance is also known, so then I can find out the value of kappa, conductivity. So this is the advantage of a conductivity cell. If I have a conductivity cell as a permanent one, the cell constant is a constant. If I fix this cell constant, I can use this cell to determine the conductivity of all the unknown conductivity solutions. So let's see one example. Cell constant is fixed, that we have seen the last problem, that is 0.219 cm raised to minus 1. Calculate the conductivity. The conductivity is not known, whose resistance is shown as 1240 ohm in the Wheatstone Bridge. So using Wheatstone Bridge, resistance is calculated and its cell constant is 0.219 cm raised to minus 1. Now we have R and G star. Then K is equal to G star by R. Substituting the values, I will get the conductivity of the solution. We have another problem. The electrical resistance of a column of 0.5 molar NaOH solution. So it's a column means it's a conductivity cell. Its diameter is 1 centimeter and the length is 50 centimeter, and its electrical resistance is found out from using Wheatstone Bridge 5.55 into 10 raised to 3 ohm. Calculate its resistivity and conductivity. By giving these diameters, we must assume that these are the diameters that is fixed as cell constants, L and A. If they are not, then we can't solve this problem. We have to assume this as their cell constants. So R is given, which might be fixed from Wheatstone Bridge, and L is 50 centimeter, radius is 0.5 centimeter, and resistance is already given here. What is G star? G star is equal to R into K. Cell constant is equal to resistance into conductivity, or K is equal to G star by R. Now what is G star? G star is L by A. L is given 50 centimeter and radius is given A. From radius, how to find A? It is diameter, it's having diameter, so the formula must be pi r square. Pi r square, area of cross section. Substituting the values, we will get, so 50 divided by, for pi it is 3.14 into 0.5 square, which is equal to 63.69 centimeter raised to minus 1. We have got G star, we have got R. Substituting for these values, we will get K. So K is, or kappa, we will get kappa. Kappa is equal to G star by R, which is equal to 63.69 divided by the value of resistance, which is equal to 0.0115. And what is resistivity? Resistivity is the reciprocal of kappa. You will have the value. Next is Selfie Questions, EC7. Write the reaction taking place in the Daniell cell when it is functioning as an electrolytic cell. Identify the cathode anode. Now it's time to pause the video, read the questions, find the answers. Once when completed, come back to the video, resume it and evaluate your answers. So if Daniell cell is functioning as an electrolytic cell, then cathode is zinc and anode is copper. That means it is non-spontaneous reaction that is happening, where zinc is getting reduced, Sn 2 plus is getting reduced and copper is getting oxidized. This is the non-spontaneous reaction because Daniell cell is now functioning as an electrolytic cell. If it is not an electrolytic cell, then it is a galvanic cell. Then the reaction will be opposite. Which is anode? Anode is copper electrode and cathode is zinc electrode because they have asked to identify the cathode and anode. Now, resistance of a metallic conductor with a length 50, say here it is metallic conductor with a length 50 centimeter and area of cross section 7.8 Newton raised to 3 centimeter square is 1 Newton raised to minus 2 ohm. So its length is given, area of cross section is given and resistance is given. What they have asked is to calculate conductance and conductivity. So with resistance, length and area we can calculate resistivity. If you know resistance, you can calculate conductance. If you know resistivity, you can calculate conductivity. So let's see. First, R is equal to rho into L by A, from where rho can be calculated as R into A by L. So substituting for the values of R and which is 1 Newton raised to minus 2 means 0.01 into 7.8 Newton raised to minus 3 means 0.0078 divided by 50. And I will get a value like this for rho. Resistance I know, which is 0.001. 0.01. Conductance is 1 by R, so just the reciprocal of that is 100 Siemens, and kappa is reciprocal of 1 by rho, that is 1 by rho value is this reciprocal, which is equal to this value. I hope you got it correct. And third question is, what are superconductors? What are superconductors? They are the materials that have zero resistivity or infinite conductivity. Examples for such materials are metals at very low temperature. Give reason why Wheatstone Bridge used for measure resistance of metallic conductor can't be used for electrolytic conductor. There were two problems in using that. One was using DC current will decompose the electrolytic solution, and the second one was we cannot connect an electrolytic solution like how we connect a metallic conductor. So these were the two differences. Okay.